And we are now live on YouTube as well.
Is it really that green space behind you, Hugh? Is that really real?
No, this is the Danube.
Okay.
Welcome, everyone. We're going to go to 2 minutes past the hour, just to let people come in fully.
Okay.
Well, welcome, everyone. Great to see you all joining us today. And I can see many people coming in from Asia, which is really impressive because it's 12 o'clock at night in Asia. And we apologize about the difficulties with the timing. And it's great to see you coming in to join us for this meeting. And so this is the inaugural virtual symposium of the International Carbene and Nitrene Consortium. And I think it's very appropriate that we have as our first speaker, Professor Michael Doyle. And the reason for that is, as you can see, he's a tremendously accomplished researcher. He's published over 400 publications, 11 patents, book chapters, and most notably, some of the really most significant books that are related to carbene chemistry, the really major books, and that everyone in the field is aware of. And as you can see, these are just some of his recent awards. Mike's received many awards, many of them for his scientific accomplishments, but also many awards for his community engagement as well. And indeed, when one thinks about all these accomplishments, it's important for you to get a feel for where Mike's career has been. Because originally he did his PhD at Iowa State and then did a postdoc at the University of Illinois at Chicago. And here we have the places where he did his academic career. So he started off in 1968 at Hope College in Michigan. In 1984, he moved to Trinity University, San Antonio, and was there till 1997. So the amazing thing, for the first 30 years of his academic career, he was actually doing his research at undergraduate institutions. And it's quite remarkable that he has 160 undergraduates as co-authors on his publications. Now, he did have some really high-quality postdocs during that time as well, but these undergraduates have really contributed fantastically to his program. And actually, he was an inspiration for me because I actually started as a small program as well. And seeing how well Mike was doing made me realize that it's not just a question of having all the facilities do everything you want to do, but actually having the motivation to drive things, as Mike has done. So in 1997, he took a switch. He actually became an administrator and went to work at Research Corporation as the president of Research Corporation, which is a big funding organization in the US. And during that time, he kept connected with academia because he also had a position at the University of Arizona when he had some spare time. And did that for 5 years and then decided to come back into academia and actually moved to the University of Maryland where for 10 years he was actually the chair of the department. And then in 2015, he moved to his current position at the University of Texas at San Antonio. So considering the massive amount of research he's achieved, it's incredible that 30 years of this time was spent at undergraduate institutions. Now, in addition to his research, Mike has done a huge amount of broader activities in the community. So if you go to his website on extramural experiences, you can see he's involved in a huge number of different organizations. And I was intrigued, what does he do with these organizations? So for example, I'm actually pretty active in the organic division of the American Chemical Society. And I know Mike has been involved with that and other issues within the American Chemical Society as well. So I decided to click one of these many possibilities, and I went for the American Chemical Society. And as you'll see on the next slide, I have to use a smaller picture of Mike. And the reason for that, yes, indeed, about 6 steps down, he does things with the organic division like I did. But you can see he's been involved in just an outrageous amount of additional activities as well. So the reason why he's had so many awards that are associated with the community is because he's been such a hugely active member and an advocate for our community. The other thing that's very noticeable about Mike is that, you know, as you can see in the top left, he can be very relaxed, but sometimes, of course, he can be very intense as well. You know, I don't know whether he's drank most of his wine, but you can see he's either preparing a paper or preparing a talk at that stage. But the thing that I remember Mike mostly is how he is at meetings. You know, you can see with old friends from the US and from China and from Brazil, smiling away, but often also really getting connected with the younger members of the community as well. He's very, very engaging across the board. But now it's time to move towards the science. And so it's very appropriate that Mike is talking about a brief history of asymmetric catalysis with diazo compounds. Obviously, I've been involved with carbene chemistry for quite some time. And actually, one of the earliest papers that really inspired me was a couple of them, back-to-back papers in organometallics in 1984, and really began to show, you know, the carbene chemistry with rhodium acetate as the catalyst, and also beginning to develop some models to explain how the chemistry occurs as well. So a huge impact at a really early stage of moving carbene chemistry from more of a physical organic type interest to really being a broadly synthetically useful process. And within a few years after this time frame, he actually began developing his first generation of his chiral catalyst as well. So Mike, we're very much looking forward to your talk, and the show is all yours.
Thank you, Hugh. I mean, it would be, okay, you have to stop sharing and then I can.
Yes, I'm doing that.
I can share. It's an honor, a true honor to actually be asked to do this and then to hear the statements that you're making that go beyond anything that I hear anywhere else. I mean, if I could have gotten that early in my career, I might have stayed even longer. But one of the benefits that I've had in all of this is working with talented people, of course, but also having the insight to actually have taken on a role in carbene chemistry at its earliest stage. It was, for me, an inspiration to see the individuals who were actually practicing that carbene chemistry in the early days. Today, I've taken the risk of talking about a brief history of this. Now, I'm going to miss many, many people who are contributing to the area, but I wanted to give a sense of the breadth of the area and some of those who actually also inspired me. So I'm going to take you through that by first taking you to this idea, this International Carbene and Nitrene Consortium. This was a concept that occurred in a dinner meeting that I had in 2015 with Chiming Che in Hong Kong. Chiming Che said to me, he said, carbene chemistry has not received the kind of attention that the breadth of its applications deserve. And isn't there something that we can do to actually tell the community that, this carbene chemistry is as really as good as any other developing area of chemistry, even at a time that, the main source of the carbenes in catalytic chemistry was diazo compounds, and diazo compounds were considered to be toxic and explosive. It was this idea that we could actually bring people together who were doing work with carbenes and eventually nitrenes to actually talk about this. The first meeting then was held approximately a year later in Hong Kong, chaired by Chiming Che. The second one, a year and a half later, this was chaired by Jimbao Wang at Peking University. And then the third was in San Antonio, a year and a half later, just at the very start of the international concern over COVID-19. We lost a number of our international speakers at that time, and finally was able to make up for that in a meeting last year at the University of Amsterdam. In the University of Amsterdam was not the December 1 to 2. That's a copy that I had for that. That was in July of 2023, and it was hosted by Bast Bruin. The next one coming up in 2025, and it's hosted by Pedro Perez. And here is basically a unveiled advertisement for this that I think should be very interesting. First of all, the speaker list is extraordinary. Secondly, it's at a beautiful resort area. And thirdly, the hospitality that we all know we can find in Spain is extraordinary. So we encourage you all to attend this really wonderful symposium. I want to start by saying I did get a inspiration to do diazochemistry, in part in looking at chemistry of nitrogen compounds early in my career. But it was in basically in 1980 that we first started publishing papers that dealt with carbene formation and the use of different catalysts. It was in the search for that optimum catalyst that led us eventually, in that short period of time, to rhodium, and particularly rhodium acetate in this system. It was at this time that you could also look around and find many others, well, a few others, not so many others, who are actually doing this metal carbene chemistry that had worked on it over a long period of time. Unfortunately, even at this time, it was difficult to find adherents, those who would actually say this is a pathway that could lead to something that was productive, useful for societal purposes. But I have listed some, certainly not all, of those who contributed in those very early days to this development. I think one of the attractions that I had, and I know many of you have, is that the simplicity of the reaction itself, a catalytic reaction using a electrophilic metal, a metal with a open coordination site, basically. Its reaction with a diazo compound, and diazo compounds are certainly not the only species that can lead you to the loss of dinitrogen, in this case, loss of nitrogen, formation of a metal carbene. From the standpoint of virtually all of our discussions, we can differentiate carbenes as being electrophilic or nucleophilic. The nucleophilic carbenes took us off into metathesis, and of course, it's particularly relevant to a discussion of carbene reactivity. But for our purposes, electrophilic metal carbenes were the species that had developed the earliest days of chemistry and actually continue today. And still, there's a lot to know about them. More recently, the idea that you could actually have something in between the nucleophilic and the electrophilic carbenes as a radical carbene has been developed. And we will not have much time to talk about that, but this will be mentioned. And it should be kept in mind that these are still partially electrophilic in their reactions, orientation, and selectivity. As Hugh mentioned, a number of books that's come out in the last 30 years have been much larger than I think what people normally would have expected. And they have helped a great deal in providing a lot of the past and projections for the future in these reactions. Classic reactions for electrophilic metallocarbenes in catalytic reactions were cyclopropanation at the very start, carbon-hydrogen insertion more recently in ylide formation, and then cycloaddition. Aromatic substitution was oftentimes thought to be basically carbon sp2 hydrogen insertion, and I think there's, for the most part, that's a very rare process. It is, in fact, a reaction that involves addition elimination. The first demonstration that one had that a catalyst with a chiral ligand could transfer enantioselectivity from the catalyst onto a product occurred in the reaction of ethyl diazoacetate with styrene, and it was done in Nozaki's laboratory by a graduate student at the time that was Ryoji Niori. Published in 1966, the cyclopropanation of styrene showed that you could achieve 6% enantiomeric excess. And this was really the beginning, not only of asymmetric catalysis in metal carbene chemistry, but certainly asymmetric catalysis overall, because this was one of the very first indications that you could transfer chirality. Nozaki, the Niori in his later publications really credited Nozaki for having the laboratory environment that made it possible for him to do this work. Notice that the catalyst that was used was a saline catalyst that was put together using the chiral phenethylamine, one amino ethylbenzene. And that was a species that was available as a chiral entity or could be produced as a chiral entity in the 1960s. We learned a lot since that time. And certainly with this as a basis, it's understandable that one would try to elaborate that ligand. An elaboration of that ligand with much larger entities, again, on the saline structure, occurred out of the laboratory of Nozaki by one of his later graduate students, Eratani. And Eratani went to work in industry rather than took the academic side, but at Sumitomo Chemical Company, he was able to show very high levels of asymmetric catalysis for cyclopropionation that resulted in the formation of silostatin, which is a commercially used at the time, and then also and subsequently, not only for a pharmaceutical drug, but also for a compound that was particularly relevant for agriculture, second generation insecticide that came from the basically the quercetic acid. And this beginnings in the late 1960s and in 1970s said, hey, there should be something else available that could actually bring us to a sense of having chiral development of chiral chemistry within the framework of chirality transfer. Now, for me, one of the great inspirations came from in a paper that was published in 1988 in Helvetica Chemical Acta by Andreas Falz. Andreas Falz, as part of his habilitation, actually developed a semicorin ligand that he put on copper. Now, no more saline ligands, but the semicorin, and he could achieve very high levels of enantiomer control. Now, a problem here and a problem with the saline ligands was not only the enantiomer selectivity, but the diastereomer selectivity. And diastereomer selectivity, as shown here, is interesting. Certainly, the dominant form is the cis isomer, but the significant amounts of the trans isomer are also present, and in these cases, also very high enantiomer selectivity. Well, this catalyzed a few people that were able to say, "Hey, this is really hot, but I've got another ligand that it's similar that I'd like to be able to use." And at MIT, Sat Masamuni, and at Harvard, David Evans was producing their own, but this now bisoxethylene, and Andreas Falz actually working on bisoxethylene. I remember Dave Evans calling me when in that, I guess, early 90s, and he said, you know, we have this ligand on this in this copper catalyst. We cannot measure the enantiomer selectivity. It's so high. The enantiomer selectivity is so high, we can't even measure it. Of course, exaggeration. We all exaggerate in these things, but it was a joy. This competition actually let us say, what we were working with rhodium at the time. Could we do anything with rhodium on this? And the idea here was, all right, we had tried early to do ligands on rhodium based on carboxylic acids. And the carboxylic acids that were chiral amino acid and derivative amino acids. And ourselves and several other groups were unsuccessful in actually seeing anything of any value from the initial studies. But it seemed that an amide system might place a chiral center just above the reacting site of the metal carbene. And therefore, it could be possible to do this. Now, the original inspiration for rhodium and rhodium acetate in particular came from Philippe Tessier, who was at the University of Liège in Belgium. His inspiration over many years of contributions showed that the rhodium was a fantastic catalyst for these. John Baer at the University of Houston at that time, working on what is the structure of the amide systems, showed that there are actually four different kinds. There are four different kind of possibilities if you actually mix a ligand with the rhodium acetate to actually displace acid. You could get all four. In our work, we saw that you could get just one as the major product. It took us many years to find out that it wasn't the only one, but it was the one that crystallized very, very nicely. It was a 3,1 isomer, and it allowed us to prepare the first enantiomer selective dirhodium catalyst as this rhodium mepi, as we called it. Well, it was interesting to use this catalyst for different transformations. And we had published a number of papers. Del Polter saw this. He said, well, I think that catalyst might allow us to make pre-squalene alcohol. So we sent him some of the rhodium MEPI, and he reported back the enantiomer selectivity was just very, very high for an intramolecular reaction on the diazo compound. The intramolecular reaction gave us the lactone, basically lactone in greater than 95% enantiomeric excess, and that was easily taken on to form the pre-squalene alcohol. We had used this system about the same time, just with rhodium acetate, and found that it did not undergo cyclopropionation to give the lactone. It underwent cyclopropionation to give a macrocyclic entity that was a macrocyclic lactone, and that led us to looking at macrocyclic chemistry. That was an interesting framework that allowed us to see for the first time that this MEPI catalyst really was mild. It was not very reactive, whereas rhodium acetate was much more reactive. This took us to other systems that said, well, how can we control selectivity? In a paper that we published about almost more than 20 years ago, we found that you could actually build a system in which you could capture the carbene and form a cis disubstituted cyclopropane compound with high enantiomeric excess. But it wasn't complete. Diastereoselectivity selectivity was itself, although high, not remarkable. And this was difficult to repeat in any other system. About the same time, much earlier than that, Hugh had actually described a system that had no problem with diastereoselectivity selectivity. If you take, in his initial efforts with vinyl diisoacetates, took styrol diisoacetate, did the cyclopropionation reaction chemistry using in this case, a chiral catalyst in pentane, knowing that this had some relevance, formed only one diastereoisomer. We were also looking at this interesting reaction from a standpoint, what about a simpler system, a double bond or a triple bond? Could we actually do selectivity between them? And it was obvious to us that reactivity had some relationship to the approach to different sites in the molecule. For the more reactive system, oops, I'm going to go back. More reactive system, for example, the systems in which you have this IBAS, a strained system in which the angle here is much longer, it lengthens this rhodium bond. You could get mainly the macrocycle. But if you used MEPI, the milder catalyst, you got mainly the lactone. Using a copper catalyst with tertiary butyl box, this is basically the approach that would have been given to us by prior work with copper. It was a mixture of compounds, and with the TBSP, which was the tertiary butyl phenyl sulfonyl prolinate catalyst that Tony McCurvey developed, it was, again, the macrocycle that is formed. So the more reactive systems gave the macrocycle, the less reactive systems gave us the 5-membered ring lactone. Now, about the same time as the other chiral entities were being put together, Nishiyama in Japan built on the pi box ligand, which he had had garnered in a postdoctoral experience that he had with Henry Brunner at the University of Regensburg. And in this time developed this ruthenium catalyst, the pi box system that showed much higher diastereocontrol control favoring the trans isomer and high enantiomeric excess in a number of different cases. Katsuki in Japan, looking also at the same time for high enantiomer control, found that it is the reaction of styrene with this case a tertiary butyl diazo acetate using a cobalt saline complex formed basically the relatively high enantiomeric excess, but very high diastereocontrol selectivity. And this brought attention to somehow, because he's working with cobalt-3, he didn't find that cobalt-2 was really the magic entity there. And the magic entity defined by Peter Zhang, already knowing that in 2005, I remember sitting in his office in 2005 when he was then at the University of Tennessee. And Peter said, I want to tell you about something of this. Cobalt catalyst carbene reactions, I think it's different. I think it's different from rhodium. I think it's different from copper. He had the idea that it was a radical species, and of course he's gone on to show that those radical species it is the magic bullet. It gives you high enantiomer control, high diastereocontrol control, and the yields are really very high in these reactions. And these kinds of insights and the mechanism for the reactions that he had himself and with Bos de Bruin has brought the cobalt porphyrin systems into an idea that these are systems that are manipulatable, that you can actually get high enantiomeric excess and novel reactions and reactivities off of these systems. And of course, when you look back into how metal carbene chemistry was developed, there's been so many people who have actually tried their luck at looking at iron carbenes, being that that's not only an earth abundant metal, but it's also a system that was much more relevant to biological systems. It was Francis Arnold who actually, by taking that porphyrin-based systems and manipulating the shield around it, could actually change this and achieve very high levels of enantiomer control in everything from epoxidation to cyclopropionation and aziridination. Now, let's go on to carbon-hydrogen insertion. We were excited in the early days of our development of these chiral carboxamidates that, in fact, one could achieve high enantiomeric excess using these for intramolecular reactions, intramolecular carbon-hydrogen insertion reactions. We had the idea that the mechanism involved a direct insertion across a carbon-hydrogen bond, and it was this that was controversial at the time, because there were other mechanisms for this, actually, and also the cyclopropionation reactions that have turned out to be things that I think we had originally found were actually, that we originally proposed are those that are now accepted. It was Nakamura that used a computational analysis on this and just confirmed that the mechanism is probably this way. It's still open to refinements and possibilities. The addition that made this effective was actually applications to real world systems. So we actually decided to attack the lignins and used the intramolecular cyclopropionation onto not the benzylic site, but the site that was the one that was found in early dirodium chemistry to be the one that was favored, in which the hydrogen was transferred from the beta position next to an oxygen, especially. And as Hughes did point out very aptly, it is having the right people at the right time that really made this happen. And as you can tell from the people on the panel, that these were people who were in the laboratory who were really made this chemistry happen. I'm just an overseer. Interestingly, I'm cocky. In 1997, I was working with Tony McCurvey and on development of a new book, this Modern Catalytic Methods, and I'm writing the chapters on cyclopropionation and carbon hydrogen insertion. And on chapter 3 is a carbon hydrogen insertion. I made the statement that intermolecular carbon hydrogen insertion reactions, they have great mechanistic value, but they're not synthetically useful, because we had tried so many of them with the chiral carboxymidates and they didn't work. And the same time that this came out, Hugh Davis reports in the Journal of the American Chemical Society, intermolecular carbon hydrogen insertion reactions catalyzed by the rhodium carboxylate, this rhodium DOS catalyst that he developed, that has been so very prominent in asymmetric chemistry from the very beginning. From that point, I mean, it was obvious that the dirhodium carboxymidates, they had high enantiomer control with diazoacetates for intramolecular reactions, but they're less reactive. So if you're going to use, if they're to be used, they are probably better than any other catalyst for the intramolecular reaction. But the carboxylates, the chiral carboxylates, of which DOS was the first representative, was more reactive and could bring you to intermolecular reactions. Now, the intermolecular reactions, I think probably the one that was most captivating to me at the beginning was to show the relative reactivity of various substrates, various carbon hydrogen substrates under mild conditions, giving high enantiomeric excess using the DOS catalyst. And this was a really inspirational contribution that laid the groundwork for understanding carbon hydrogen insertion reactions. At the same time, Hugh was doing this applications that was saying, is the metal carbene chemistry, is it relevant to our society? Because, so much of the pharmaceutical companies would not even touch diazo compounds in chemical reactions, because there was such a fear of being toxic and explosive. And here he had taken systems, fairly complex systems, and made representative compounds that are of critical interest in the pharmaceutical field. And that was actually the beginning of something that I'll just impart on you, a development of additional chiral dirodium catalysts that were able to do very high levels of enantioselective and site-selective CH insertion reactions. Using the DOS catalyst, able to actually see that, in systems in which you have ethyl and methyl, you could choose ethyl over methyl. And if you change to this very bulky triaryl cyclopropane carboxylate, you could actually find yourself dealing with site selectivity at the primary position. this went on to, beautiful set of publications showing first the secondary site selection, a tertiary site selection, and primary site selection in these cases, giving you an evolution that tells you a lot about the field. There's a general feeling, I think, overall, that if you can identify a catalyst, if you actually can find a catalyst that is unique and that can do something that is highly selective, better than anything else, that gives you a position in the field that is truly memorable. And of course, it brings in a lot of money and research grants and a lot of things that are certainly beneficial to the research in the area. But this is a scheme that shows Hugh Davis's pattern of bringing catalysts through a period of basically, this is more than 20 years, to its present state, where you can have very highly site selective reactions in these chemical transformations. Attempts to do this with cobalt porphyrin catalysts have thus far been acceptable, only in the intramolecular reaction chemistry. The intermolecular reactions have not proven yet to be successful in these reactions, but the intramolecular reactions give you very high enantioselectivity and the site selectivity, forming 5-member ring compounds in that intramolecular reaction. The evolution of these two iron porphyrin systems that took place at Francis Arnold's laboratory showed that you could do the site selective reactions to form these cyclopropane systems with a high, form the lactone systems with a high degree of selectivity and give this as the sole product in the reactions. This is another evidence of the effectiveness of these systems. Interestingly, we know that if we had taken this substituted phenylpropyl system and showed that you could actually make the corresponding lactone by intramolecular cyclopropionation using carboxamidates. What the enzyme catalysis does is goes beyond that. Something that is, I think, is really spectacular. Instead of forcing this to a 5-membered ring, which is mechanistically the most favorable site for these reactions, in this case, by using a variant of the iron porphyrin system, her group was able to show that you could form a 6-membered ring compound. And of course, from these, all kinds of things are possible. In these various drugs of a variety of sorts are certainly available by using this kind of chemistry in the enzymatic platform to actually go beyond that. And that's one of the challenges. There's certain things that the porphyrin systems can do that can't be done by the non-enzymatic processes, but there are others that are done most favorable by the others. Illage transformations were another development that I think has captivated metal carbene chemistry, and it was, I think, our interest in just seeing that if you could do sigmatropic rearrangements that led us to showing for the first time that you could achieve high enantiomer control in a reaction that was catalyzed by a chiral rhodium complex, giving 98% enantiomeric excess of that system. We also had done that with a Stevens rearrangement reaction showing high enantiomer control, relatively high enantiomer control. This was at a time that I remember undergraduate student of mine who was doing his PhD work at Harvard, saying he was in E.J. Corey's class. And in E.J. Corey's class, he had, knowing that what we had done in this process, he had proposed that you could use a transition metal to do other ylid transformations in a chiral fashion. He received the paper back and it had a red line through that. It's just impossible. It was very, very interesting to see that most people actually didn't even try to do enantioselective reactions at these times on ylid transformations. And they've now become a big area. Wenhao Hu is probably one of the most notable in the way he has taken it. He makes the ylid by using rhodium catalyzed reactions to actually form a nitrogen or oxygen ylid, and then using a chiral Bronsted acid can actually affect, in this case, is using the chiral Bronsted acid, high enantiomer control by the subsequent reactions, whether it's a hydrogen assertion or another reaction. The versatility of this is shown in part in a review by Rene Koenig, who actually, that shows that these rearrangements, these ylid transformations, are just now, there's still a ripe area for exploration because there's so much that hasn't been done relative to the things that have been done. And so that seems to be it's a continual hot area. Now I want to take you to an area that had been previously not really known, but discovered only in the last 15 years. It came from a diazo compound that was first made by Hugh Davis. We call it the enol diazoacetates. It has a silo-protected oxygen here, and A can be an alkyl group or hydrogen, or even an aryl group. It was our thought that if you actually make this system happen, you could actually generate metal carbene in which you have electrophilic center at the vinylicus position, something that the term vinylicus I've used very often after Hugh Davis first used it. Now we could actually take this vinylicus reaction, do a electrophilic nucleophilic center attack, and leave us with a electrophile that would actually complete the reaction by taking on a system, a stabilizing oxygen that would complete the process and give us this unit as able to place 3 carbons in a cycloaddition. Our first shot at this was 3+3 cycloadditions, which we thought that it could work well. 3+2 cycloadditions were also thought to be important, but the most difficult one that we thought would be of interest would be the 3+1, making a cyclobutene by having a carbene react with a carbene, basically. Well, with dirodium catalyst, we published this. I mean, you can make enormous number of heterocyclists, high enantiomeric excess, high yields in these reactions, and in diaster selectivity, reasonably very high diaster selectivity. So it worked well. In our consideration of this, rhodium is an expensive metal, and there have been times where the cost of dirodium has been dirodium acetate, especially, has been very, very high. So we said, well, could we do the same thing with copper catalyst? And in fact, many of the same reactions could work well with copper. It's still not evident that all of them can be done with copper that had been done with rhodium, but it's very close to that. So the 3+2 cycloaddition reactions, we've also looked at that. again, high enantiomeric excess. Hugh Davis has looked at that, found the same sorts of things in different ways. The systems work differently if you have a vinyl diisoacetate that's not an enol diisoacetate. But you were brought to the last stage of the process, and that was carbon hydrogen and the formation of a four-membered ring. To get there, the four-membered ring, we could use in this. Excuse me, I've got to get there. Four-membered ring, we could use a sulfur ylide as for the diazo transfer. We had also used a real carbene. We used the Grubbs carbene, and the same reaction takes place, but this is using a metallocarbene is an expensive process compared to the sulfur carbene. So we could actually do this to form the four-membered ring acetine, excuse me, not the four-membered ring cyclobutene system that had high diastereocontrol, high enantio control. Using a nitrogen sulfur ylide, we could do the same thing to form the azotine ring. In both cases, these reactions form a reactive intermediate. Both of them have a system that if you remove the TIPS group, you form the corresponding ketone. This is a beta ketoester, and it's set up for reverse Claisen reaction. These reverse Claisen reactions are virtually quantitative and offer another possibility. Throughout the history of diazochemistry, numerous changes have been made to enhance the applicability and the versatility. Of course, ethyl diazoacetate were already in the 1900s. Since the 1970s, the acceptor diazo compounds were being used to increase selectivity. In some cases, that selectivity did increase, but it was the introduction of aryl and vinyl diazoacetates, mainly in work that Hugh Davis has done, that brought us to a sense that there's a whole set of reactions that you could do with higher degree of selectivity and reactivity, especially with dirodium catalysts. Enol diazoacetates that I pointed out are really particularly special for cycloaddition reactions. And most recently, we've developed oximido vinyl diazo compounds that have given us ability to actually further expand the structural variety of diazo compounds that are available. They come to us, as Hugh would, he put a smile on his face by saying it comes to us from a vinyl diazoacetate to start with, but these reactions form a triazine 1 oxide that upon reaction with a mild base give us a new diazo compound in which all of the positions that are shown here in these colored balls it's possible to actually formulate new structures. And we've shown just recently that these compounds actually undergo high enantio control and cyclopropionation, NH insertion, OH insertion, and in cycloaddition reactions. In another piece of work that is about to be published, taking these 1, 2, 3 triazines, treatment with base, the base being a diazo compound, removal of that acidic hydrogen allows us to form any variety of compounds of this sort that are just now ripe for investigation. And we hope that we can show that there are a number of things that are possible here that would not be possible with the traditional diazo compounds. I think we also have to remember that diazo compounds are not just set up for formation of metal carbenes, that any electrophile can react with that, either directly attack at the diazo carbon or at the vinylogous position. And new reaction chemistry can come from that. We've just completed a a set of reactions showing that if you start with just a vinyl, and these are virtually any vinyl diazo acetate, electrophilic additions can give you a new diazo compounds that are subject to migration reactions, and that allows the formation of new compounds that are potentially valuable in synthetic organic chemistry. Well, I am who I am today because people like these. This is a group of my students who have worked with me, either postdocs or undergraduates or graduate students who I have benefited from. It's their genius that has made all of this possible. And I'm particularly grateful to you today for taking the time from your schedule, even as late as, this is early in the morning of tomorrow for us, of being with me today. So thank you very much. And I'm happy to answer any questions.
Great talk, Mike. Really excellent. So we've got some interesting comments and questions for you. Let me read them to you. First of all, we have an interesting provocative question from an anonymous attendee. So Professor Doyle, thank you for your seminar. I would like to know, as biocatalysis is slowly becoming the next big thing, where do you see transition metal catalysis going in the future, both in academia and in industry?
Yeah, the biocatalysis that, of Francis Arnold is really, it's taking off. There are a number of people, that are engaged in that. And it has its role. It is yet to establish itself as being able to be something that can actually do something in bulk. Being able to do something that would, if you need a kilogram of something, I'm not sure that that's the way to do it. But then for that, then the traditional systems which we can now manipulate, and the manipulation is coming both on the side of being able to design not only the ligands for the reaction, but also investigate the new metals. I'm sure we haven't discovered all of the metals that are there. We haven't even touched the lanthanines and other systems like that.
Okay. John McGuire is saying, Mike, fantastic overview. Well done on all your tremendous contributions in carbene chemistry. Anita McGuire.
Thank you.
And then Jenbo Wang wants you to be aware that he's still awake even at this time. And he's saying, Mike, this is a great talk. Thank you very much for your long-standing and great contributions to the field of carbene chemistry. Wish you will remain healthy and continue being active in this fantastic field.
Thank you very much.
And I want to add something in that you are very generous about how you talked about our work, but I must tell you that your early work in asymmetric catalysis was the inspiration for all of us to bring rhodium into the field. So, and I was pleased you added that quote in the book. And the great thing is it takes longer to publish a book than it does to publish a paper. So
no, and sometimes it is something like that actually it's a catalyst for making something happen. If you, I think we refrain, and publishers don't allow this to actually give a personal opinion that it could actually catalyze others to do that. If we had more of that, I think we'd have a more interesting time.
Well, once again, Mike, thanks for a really, another comment from Pedro Perez. Mike, great talk, and thanks for that sentence about the intermolecular CH activation in your book. Aha, it was a real challenge for us.
Yeah.
And then one of your previous anonymous attendee, this is one of the many of your former undergraduate students who was so grateful to have had your wonderful training and mentorship. Thank you for a great seminar.
Thank you. Thank you. I'm honored.
And Dorota is saying, Mike, thank you, great seminar.
Okay. Yeah, enough is enough. My head is getting so large.
Okay, great. Well, at this stage, again, thank you everyone for joining us. So we had up to about 170 people come online, which is fantastic. DJ, do you have questions from the YouTube you wanted to mention, or anything else?
No, I think we're good to go.
Yeah, excellent seminar, Mike, and thank you for putting all the work into perspective, and congratulations to you going forward. Someone's asking about, will a recording be available? That will be up to Mike. So we'll keep in touch about that.
Yes. Yes.
I think it will be.
Yeah.
You may want to send me an email so that we can we know who's requesting too.
Sure.
Okay, well done, Mike. Congratulations.
Thank you.